Welcome to the video lecture on composition of functions. This video lecture is going to talk about how to compose two functions together and also talk about other ways to combine two functions together to create a new function. The most obvious way to combine functions would be to just use our normal operations like adding two functions together, subtracting them, multiplying them, or dividing them. So let's talk about that process first. The notation that you'll see when you're trying to add two functions together would be this notation right here. Parentheses f plus g of x means take f of x and add it to g of x. So you would just add their two rules together. Now when we do these new creations, we want to take an interest in their new domains as well. So the domain when you are adding two functions together would be the domain of f, and that's what this d of f means. So we're going to take the domain of f, and we're going to take the domain of g, and we're going to intersect these two domains. So the intersection of the two domains would be the domain of this sum. Likewise, the notation for subtraction would be f minus g of x, and you just subtract f and g, and their domains would just be intersected as well. Similarly, for multiplication, you would multiply the two rows together, and the domain is the intersection of the two individual domains. And then finally, for division, you're just going to divide f over g, and the notation would be f over g of x. And this time, you still want to intersect the domain of f with the domain of g, but you also need to consider where the bottom function, which in this case is what we're calling g of x, where that g of x might equal to 0. So you're going to take the intersection of f with g and also exclude any x values where that denominator might be 0. And that's because we don't want to ever divide by 0. So let's try a couple of examples. For this first example, we're going to let our function f be the square root of 1 minus x, and we're going to let g of x be the square root of 9 minus x squared. So first, let's just practice evaluating these two functions. So we want to evaluate f times g at -2. And you have to remember that this notation means take f at -2, take g of -2, and just multiply those two results together. So how do we find f of -2? Well, we just go up to f's rule, and we're going to plug in -2 wherever we see that x. So this would become square root of 1 minus -2, which is going to simplify to the square root of 3. Now for g of -2, we're going to do the same thing. We're going to substitute in -2 in for this x. So this would become square root of 9 minus, and I'm going to use parentheses here, -2 quantity squared. The negative inside of the parentheses gets squared away, but the subtraction on the outside does not. So this becomes 9 minus a positive 4, which subtracts to a square root of 5. So we got square root of 3 for f, we got square root of 5 for g, and for the product, we just multiply these together. Since they're both under square roots, we can multiply the 3 and the 5 and get square root of 15, and that's a simplified radical, so we can leave our answer like that. Okay, let's try a quotient. So now we have f divided by g evaluated at 0, and this means take f at 0 over g at 0. So this time we're going to plug in 0 for x into our rule for f, so square root of 1 minus 0. And on the bottom we're going to plug in 0 for x for g, so that would be square root of 9 minus 0 squared. So the numerator simplifies to square root of 1, the denominator simplifies to square root of 9, and each of those are perfect squares, so it reduces to 1/3. Okay, so know how to evaluate these different functions, their products, quotients, sums, and differences, and know what that notation looks like. Now we're going to take a look at what the domains of the difference and the domain of the quotient would be. And we're going to refer to the same functions that we had earlier. So remember that f of x was square root of 1 minus x. and g had as its rule square root of 9 minus x squared. So to find the domain of the difference, you could actually find the formula for the difference if you wanted to by just subtracting these two square roots. But to find the domain of the difference, you need to find the domain of f and the domain of g. And then we're going to intersect those two different domains, and that will be, by definition, the domain of the difference. So let's start with f. How do you find the domain of the function square root of 1 minus x? Well, there's a couple things you look for when you're talking about finding domains. The two probably most common things that could go wrong for domains is dividing by 0 or taking the square root of a negative number. And since we don't have any fractions here, we don't have to worry about ever dividing by 0, but we do have square roots. So we want to make sure that for the domain, and for this square root function to actually exist, whatever expression you see under that radical, you need to make sure that it's either 0 or something positive. You never want it to be negative. So I'm going to take this expression 1 minus x, and it will be okay as long as that expression gives me something that is greater than 0 or possibly equal to 0, because square root of 0 does exist and square root of a positive does exist. We just don't want to allow square root of a negative. So now we have this restriction. Let's go ahead and solve it for x. So I'm going to add x to the other side. And to me, this is a little bit backwards. We tend to like to have the variable on the left side of the inequality. So I'm going to flip it around and put the x on the left, the 1 on the right, and therefore I have to flip the inequality around as well. So this would be all the x's less than or equal to 1. And if you visualize that on a number line, that's a closed circle and all these x's going to the left. Or if you wanted to use interval notation, that would be minus infinity up to 1 with a bracket. So that's the domain of f. Okay, now we're going to do the same thing, but for g. So we have 9 minus x squared, and we want to make sure that this expression under the radical for g is also positive, so greater than 0, or possibly equal to 0. Now this one's a little trickier to solve because it's not a linear inequality because of that square. So one easy way to figure out where this inequality is true is to do it graphically. What does the graph of 9 minus x squared look like? Well, we know that x squared is a parabola pointing up with its vertex at the origin. Because of the minus, there's a reflection over the x-axis, and the 9 on the side, since it's a positive 9, that's a shift up 9 units. So this is just going to be a parabola that's pointing down because this a term or this coefficient of x squared is negative, and it's been shifted up 9 units. So instead of being centered at the origin, now it's going to be up at a height of 9. So it would look something like this. Now it's important for us to know where this parabola is greater than or equal to 0. So where would it equal to 0? That's going to be where it hits this x-axis. So two key points to know about would be where does this parabola actually equal 0? And where does 9 minus x squared actually hit 0? Well, that you can solve. Just add that x squared to the other side. Take a square root of both sides. Remember your plus or minus. And that tells us that these two x-intercepts would be negative 3 and positive 3. So where is the graph of this parabola greater than or equal to 0? Well, it's greater than 0 at all of these points on the graph, which corresponds to all of these x values in between negative 3 and 3. So our domain for g is going to be all these x's between negative 3 and 3. And what about those two endpoints? Should we include them? In this case, yes, because we are allowing the parabola to actually equal 0, so we do want these to be closed circles. So the domain of g would be all the numbers between negative 3 and 3 and including negative 3 and 3. So if you were to graph that on a number line, let me do it below this one over here, that interval would look like this: -3 up to +3, closed circles around the endpoints, and shading in all those x's in between. Now the reason I lined these two number lines up is because now that we've found the domain of f and the domain of g, to get the domain of this difference function, we need to intersect these two sets. So it helps to line them up like this so that you can kind of see where the intersection is. And by intersection, that means where are these two number lines shaded in at the same time. And you can hopefully see that that happens right here. That's the only place where both number lines are colored in. So that would be from -3 up to 1. Both number lines are colored in. And how about the endpoints? Are the endpoints shaded in for both graphs? Yes, because they're both solid dots. It's included up here, -3 is included, and 1 is included. -3 is included down here, and 1 is included as well. So that means we do want to include the endpoints as well. So our final answer, the domain of f minus g of x, would be the interval -3 up to 1, including those two endpoints. Okay, so we found the domain of f, we found the domain of g, and then we looked to see where their intersection was. All right, let's try this again, but this time we want to find the domain of the quotient of f and g. And luckily for us, we've already done the majority of the work. We already know where the intersection of these two sets or these two domains is going to be. We already figured all that out over here. So we know that the domain of f was -∞ to 1, and the domain of g was -3 to 3, and the intersection of these two sets, and remember this upside down U shape means intersection. The intersection of these two sets is the answer that we got for this last example. So that was from -3 up to 1. So if you remember, let me scroll up here for a moment. The domain of a quotient function is the intersection of the domain of f and g, just like we did already, but we also have to exclude any place where the denominator function, the g function, is equal to 0. So what we're going to need to do is we still need to exclude any place where g of x might equal to 0. So remember, g of x was this square root of 9 minus x squared. And where did that equal to 0? Well, it's going to equal to 0 when this inside quantity equals to 0. And 9 minus x squared equals to 0. Remember, we solved that already. We take our square roots at plus or minus 3. So we want to take our intersection, which was up here, so -3, 1, and exclude plus and minus 3 from that. Well, +3 is not even included, so it's already excluded from that intersection. But -3 is this endpoint, and right now we have it included because we have a bracket. So to exclude it, all we would have to do is use a parentheses around it, and now we're not including the -3 at all. We still want to keep the 1, so use a bracket around the 1, but we don't want the -3. So this would be the domain of f divided by g. So it looks very similar to the last answer. We've just left off the left endpoint. Okay, so far we've talked about how to combine functions by either adding them, subtracting them, multiplying them, or dividing them, and their domains come from just the intersection of the two individual domains. What we're going to talk about next is the name of this video lecture, composition. So now we're going to focus in on the composition of two functions. And there's a special notation for this. If you want to talk about a composition of two functions, you will see this little open little round circle, and that means composition. Doesn't mean multiply, it means composition. So if you see that little circle between your f and your g, that means we want to compose f with g. Now, what does composing two functions mean? Well, it's kind of a two-step process. When you're composing function f with function g, what you're going to do is you're going to take the g function first, and you're going to find out what its output is, and then that output becomes the input into f. So first we're going to do g, then we're going to plug that answer into f. So whenever you see f composed with g in this particular order, so f coming first, then the g, you're actually going to use the second function first and plug it into the first function. Okay, so the composite function, or sometimes just the composition function, is denoted by this little circle notation, f composed with g, and there's several ways you can say it. You could say f composed with g, or you could say f of g of x. That's what this notation typically is interpreted as, f of g of x. Or you could just see it written as the composition of f and g. And this is its definition. So you're always going to take whatever that second function is, do that one first, and then plug that answer into the first function. Now, to find the domain of a composition, first you're going to figure out a formula for what the composition looks like, and then you're going to take the intersection of the domain of that formula with the domain of g of x. So we're going to take the domain of the composition and the domain of just the input function, the g function, and we're going to intersect those two together. So let's try this out. So here are my two functions. F of x is this rational expression, x plus 1 over x minus 2. G of x is x minus 3 over 2x plus 5. And we want to find the domain of each. Now, unfortunately, the only way to find the domain of a composition is to actually find the formula for the composition first and then work from there. So let's look at this notation. I know that this means composition. This means f composed with g at x, because we're taking g, figuring it out, and then plugging that into f. So this is how you would figure out what this rule is going to be, and it's a little bit tricky. What we're going to do to figure this out is we're going to not use f yet, but we're going to go ahead and figure out what g of x is. And g of x is just given by this rule right here. So g of x is x minus 3 over 2x plus 5. Now here's the tricky part. This whole fraction then becomes the input into f. So wherever you had x's before, now we're going to take this entire fraction and put it in for this x, and take this entire fraction and input it in for this x. Because the rule for f says to take whatever your input is and add 1 over whatever your input is minus 2. So this is what it would look like. We're going to take our input, which is this whole big fraction, and we're going to add 1 to that, and then we're going to divide all of that by whatever our input is, which was that whole fraction, and we're going to subtract 2. So since f and g were both fractions, we get this fraction within a fraction, which is called a complex fraction. So how do you go about cleaning this up so that it's a little bit more manageable to deal with? Well, there's a nice little trick here, and that is to look at all your denominators. I've got this denominator and I've got this denominator, and they're the same. So what we're going to do is we're going to multiply the top of this fraction by that common denominator, 2x plus 5. Now when I take this entire fraction times 2x plus 5, the 2x plus 5 cancels out. And all we're going to be left with is just this numerator, x minus 3. Okay, now if I go back and go to the second part of this numerator, now I need to take 1 times this whole common denominator. This 1 does not have a fraction in it, so nothing's going to cancel out. So we're just going to take 1 times 2x plus 5, which keeps it 2x plus 5. Alright, let's try that again in the denominator. So now we're going to take this fraction, x minus 3 over 2x plus 5, and multiply it by 2x plus 5. So the 2x plus 5 in the bottom cancels with the 2x plus 5 that we're multiplying by, and it's just going to leave us with this numerator, x minus 3. And then when I go to my second part of my fraction, we already did this. Now we're going to take negative 2 times this whole common denominator. And again, there's no fraction, so nothing's going to cancel out. So it's going to stay minus 2 times, and notice I'm using parentheses here, times this entire 2x plus 5 quantity. So we will need to distribute there. So let's go ahead and do that. And while I'm at it, I'm going to clean up a few like terms in the numerator. So I have an x and a plus 2x, which is 3x, and I have a minus 3 plus a 5, which would be 2. So there's my numerator. In the bottom, if I distribute, I'm going to get a negative 4x and a minus 10. And if I clean up my like terms in the denominator, that's going to give me x minus 4x, which is negative 3x, and negative 3 minus 10 is negative 13. So this is our sort of cleaned up rule for what the formula would be for our composition of our two functions. Now that's not actually our answer, because they didn't want to know what the rule was. They wanted to know what the domain was. So this is how we're going to find our domain. Once you've figured out what this formula is, we need to find the domain of this rule. Because it's a fraction, the only thing we have to worry about in terms of domain is possibly dividing by 0. So to figure out the domain of a fraction, all you have to do is take whatever that denominator is and find out when would it equal 0. So let's go ahead and solve this. I'm going to add 13 to the other side, divide by negative 3, and this gives me x equals negative 13 thirds. Now remember, that's the bad point. If x is equal to negative 13 thirds, then I will end up dividing by 0. So we want our domain to be everything but negative 13 thirds. And the easy way to do that is to just use that not equal to symbol. So the domain of this formula is everything except negative 13 thirds. Okay, now that's not the only answer. Remember our rule from up above. To find the domain of a composition, not only do you have to find the domain of the formula, but you also have to consider the domain of the input function. Remember that this is a two-step process. We have to be able to plug something into G first, get an answer, and then plug that into F. So if G doesn't exist in the first place, then there's no way that the composition is going to exist at all. So we have to make sure that the G function is valid before we can do the composition. So let's look at G's rule up here. What would be the domain of G? Well, it's a fraction, and with fractions, like we said a minute ago, the only thing you have to worry about is possibly dividing by 0. So to find the domain of G, we're just going to take its denominator and find out when does it equal 0. So I'm going to solve for x by subtracting 5 and dividing by 2. And negative 5 halves then would be the bad point. So the domain of G is everything except negative 5 halves. So what we want to do for our final answer then is intersect these two domains. So the domain of the formula was everything except negative 13 thirds. The domain of G was everything except negative 5 halves. So the domain of our final answer here is going to be all reals. If you want to write it out in words, you can. All reals except these two bad points. negative 13/3, and negative 5/2. So we just want to exclude both of those from our domain. Okay, so you find your formula, figure out where that formula might become undefined, go back to your input function, which in our problem was g, and find the domain of that function, and then your domain would just be all values in both of those sets, so the intersection of those two sets. Let's try one more example. We're still using the same two functions, f and g, but this time we're going to find g composed with f. So how is that different from the last problem? What's important to notice here is that the order is different. This time the f is coming second, which means you're actually going to evaluate it first and then plug that into g. Order matters when you do compositions. So this time our input function, our initial input function is f. So we're going to have to worry about what the domain of f is when we try to figure out the domain of this whole thing. So let's go ahead and figure out what the domain of f is going to be. Here's f's rule. It's a fraction. So where is this going to become undefined? Wherever the denominator hits 0. And x minus 2 hits 0 at 2, and that's the bad point. So the domain of f is going to be all x's except for 2. So we already know part of what our domain should be, the domain part that is going to make f valid. Now we still need to figure out what the formula for all of this is and find its domain, and then we're going to intersect these two solutions. So let's go ahead next and find the formula for g of f of x. So the way that this composition works is first you need to use f's rule first. Well, what's f's rule? F's rule is x plus 1 over x minus 2. That's what f of x equals. Now that we know what f of x is, we're going to plug that into g. Now this is the tricky part. So you look at g, and g is this a whole other fraction. And according to g's rule, you take whatever the input is, subtract 3, and then divide that by 2 times whatever the input is plus 5. So what we're going to have to do is take this entire fraction, which is our input, and plug it in for these two x's, right here and right here. So this is what it would look like. Instead of x minus 3, it's going to be this fraction minus 3. And instead of 2x plus 5, it's going to be 2 times this fraction plus 5. Okay? Now if you want, you don't have to do this, but if you want, you can distribute that 2. Remember that this 2 is like a 2 over 1. So you'd multiply top times top over bottom times bottom, and when you multiply the two tops, you do need to distribute. So this would be x plus 1 over x minus 2 minus a 3, and then 2x plus 2 over x minus 2 plus 5. Now it's still pretty messy because it's a fraction within a fraction, so to clean it up, we're going to perform our little trick of multiplying by whatever our denominators are. And our denominators are both x minus 2's. So I'm going to multiply x minus 2 on the top and x minus 2 on the bottom. So when I do this first fraction times x minus 2, the x minus 2's cancel out, and that's just going to leave me with this numerator x plus 1. Then when I go and I multiply the negative 3 times x minus 2, there is nothing that cancels out. So we're going to just have this minus 3 left over and this x minus 2 left over as well. And we'll distribute that in the next step. Now let's go to the denominator. Now I'm going to take this fraction times x minus 2. So they both cancel out, leaving me with just the 2x plus 2 from the top. And then when I go to my second fraction, 5 times x minus 2, there is no fraction there, so it doesn't cancel out, so that plus 5 stays put, and the x minus 2 in parentheses stays put. So here's what we've got so far. We need to distribute. So let's go ahead and distribute. We get a minus 3x plus 6. And on the bottom, when we distribute, we'll get a 5x minus 10. And let's clean up our like terms. So in the numerator, we get negative 2x plus 7. And in the denominator, we get 7x minus 8. So we've done all this work, and the reason we've done this work is because we want to take this final formula here and figure out what its domain is. The domain of this composition, and it's actually the G composed with F. I had my order wrong. So what would be the domain of this formula? Because it's a fraction, all we have to worry about is where that denominator equals 0. It doesn't matter what the numerator is at all, it's just where that denominator is 0. So if I solve this for x, I'm going to get x equals 8/7, and that's the bad point, so we want to exclude it. So for our final answer, what's the domain of the entire composition? It's this domain, all x's except for 8/7, intersected with this domain, the domain of f, which was the set of all x's except for 2. So all that's going to imply is that our domain is all real numbers, or all reals, except both of those bad points, which was 8/7, whoops, sorry, except 8/7, and the other one was 2. Okay? So those two problems were almost identical. Alright, the last example here is just to kind of work in reverse. So this time what I'm giving you is the already composed formula. So f of g of x, after you compose these two functions together, the formula that you come up with is 1 over square root of x plus 3. And what I want you to tell me is what must those original two functions have been so that when I compose them I get this rule as my answer. And I'll warn you right now that there's a couple of correct answers here. There's more than one answer, so I would accept many different possibilities. So one way to think about this is if we're looking for f composed with g, that means we're taking some expression, some stuff, and we're plugging that into f. And this is what we want to end up with. So sometimes what I'll do when I'm trying to figure this out is I'll think of this as different pieces. And if you were to evaluate this, what would be, say, the first piece that you would probably evaluate? Like, for example, if I was going to let x equals to 4, what would I do first? Well, I'd plug 4 into my square root and I'd try to simplify square root of 4, right? So that's usually what I would pick as my first guess for what g of x is going to equal. So let's let g of x be that square root of x piece, just that first piece. So then if I wanted to take f and compose it with g, then that means I want f evaluated at square root of x. So what would the function for f have to look like so that when I plug in square root of x, the answer gives me 1 over square root of x plus 3 back again? Well, think about it this way. We would have to see in our formula something like this. If f was the function 1 over stuff plus 3, then if I were to input in square root of x, then that square root of x would fill right inside of that box. So the function for f must be 1 over input plus 3. Now how would you write that using f of x notation? F of x notation would just be 1 over the input x plus 3. So there's our guess for f, and here was our guess for g, and let's check. Let's check that these are the correct choices. So if I let f of g of x, if I try to find f of g of x, the first thing that I would need to do is evaluate g of x, and we're saying that g of x is square root of x. Then, once I have that, we would want to go to the rule for f, which I have down here, and substitute in this square root of x wherever I had x in f's rule. So this would become 1 over square root of x plus 3. And that is what we wanted to end up with, so that seems correct. So if we let g be square root of x and f be 1 over x plus 3, then it does work. Are there any other ways that this could work? Let's try one more possibility. So remember that our final rule is supposed to be 1 over square root of x plus 3. So a lot of times when I look at these, I look for those pieces again. And in the last solution, we let the square root of x be a piece. Well, one other way you could do this is you could let this whole denominator be a piece. You could let this whole denominator be your g of x. So let's let g of x this time be square root of x plus 3. Then what would f of x have to be? What do you do with this square root of x plus 3 to get this rule? You have to do 1 over it, right? So the rule for f must be 1 over its input. In other words, 1 over its x. So these are my guesses. Let's check. Let's check to see if these are valid choices. So let's find f composed with g of x. So first we need to know what g of x is, and according to our guess, g of x is square root of x plus 3. And that answer then gets plugged into f, and f's rule is 1 over its input. So we would need to go 1 over this whole input, and that's what we wanted to get, so that works. So we had two different solutions depending on how you assigned your pieces, but both would be considered correct. Alright, good job. That concludes our lecture on composition of functions. Good luck.